Hi, hi to everybody. In this lecture video, we are going to be dealing with potential and fields. And after doing this chapter or this lecture, you will be able to use the scalar and vector potential in Maxwell's equation, and you will also be able to understand the solution of inhomogeneous wave equation, and you will also be able to derive the equation of the retarded potential, and you will also be in a position to derive the Jeffimenko's equation, and you will also be able to derive the linear charge potential, which is nothing else but the potentials of a moving point charge, and you will also be able to derive the fields of a moving charge. And from there, you are also going to be expected to solve the problems on the above. Now, let us just start with the potential for formulation. Now, what we seek the general solution to a Maxwell's equation. And the Maxwell's equations are just given by this. And as you remember in the previous chapters, when we talk about for an example, the charge density, the charge density was always a function of the position. And the current density as well was just the function of position. Now, in this case, what we want to do, we want to find a general solution whereby this charge density is the function of position and time, as well as the current density is the function of the position and time. So that's what we want to do. We want to get this if we know the charge density is a function of position and time. Now the question will be, what will be the electric field and the magnetic fields, both as a function of R and T. Right. Now, let us just go back to electrostatics. You remember in electrostatics, when the charges are not moving, the curl of electric field is a conjugative vector, is a conjugative. What does that mean? When the charges are not moving, the curl of electric field can be given as 0. Now, if we have a curl of electric field is equal to 0, therefore that implies that we can write an electric field as a negative gradient of a scalar potential. Good. We can therefore be able to write, if the curl of a certain vector, say if E is equal to 0, that implies that we can write that vector as a negative gradient, of the potential. And this is what you know from your previous class. And this is a scalar. This is a scalar potential. This is a scalar potential. This is a scalar potential, because when we talk about the magnetic field B, is just given by the curl of a vector potential. So I just want you to know this is a vector potential, this is a vector potential, Therefore, electric field is defined in terms of the negative gradient of a vector potential, while the magnetic field is actually defined in terms of the curl of a vector potential A. So this is the difference that I wanted you to see and know, or actually to remind you from what you have done in the previous classes. Now, however, in electrostatics, the curl of electric field is no longer 0, but the curl of electric field is just given by, for an example, the Faraday's law is non-zero. It's just given by the Faraday's law, as you can see it there. Now, but the B remains divergeless because the magnetic field, the B field, is divergeless, and as a result, it can still be written as the curl of a vector potential A. Now, putting this into a Faraday's law number 3, if we want to put this into a Faraday's law number 3, what are we going to have? We are just going to have a curl of E, but the negative rate of change in magnetic field B. Whenever I see B, I'm going to write this. So this is what I'm going to write. Now, or I can just take the curl, and if I take the curl, this is what I'm going to have. And from here, I will also want to write this equation here, if I compare this equation with that one here, which means this equation here, this can be written as a gradient of a certain a negative gradient, because now if I have the curl of E of vector E is equal to 0, and if I have a curl of this is equal to 0, then I'm saying I want to write the electric field as a gradient of, because its curl is 0. Now even in this equation here, the curl of everything here is 0. Therefore I can write this as a negative gradient of a certain scalar potential. Right, this is what I'm actually doing. Now, in this way, what I want to do, I want to write the electric field in terms of the scalar potential and the vector potential. That's the aim of why I am doing this. Now, in that case, if I want the electric field in terms of the scalar potential, not bold, vector, scalar, and bolded is a vector. In terms of a vector and the in terms of the vector potential and the scalar potential is just given by this equation. Right. Good. But what is very important is the fact that when the vector potential A is constant, you can just see that this equation will just go back to that electrostatics equation. Right. This is what is. Now, but however, the magnetic field is always the curl of A. The curl of A, a vector potential A, we know that the magnetic field is a curl of a vector potential A, and the electric field is just given by this equation that we've just derived. Now we just want to see whether these two fields satisfy the homogeneous Maxwell equation number 1 and number 3. Now in this case, let me just go to show you that this satisfy the Maxwell equation number 2, and then you will also do the same for 3. Now in terms of 2, because this is just this very simple one, I have the divergence of the magnetic field. The divergence of the magnetic field is equal to 0, but I know what is B. The B field is just given by the curl of vector potential A. Now in here I'm just going to write the divergence of the curl of A, because this is magnetic field. This must give me 0. And I hope you still remember that the divergence of a curl is always 0. The divergence of a curl is always 0. And then in fact we can be able to prove this. We can be able to prove this. First of all, when you want to prove this, you will have to take the determinant of that. You will have to take the determinant of that. You will have to take the determinant of that. And I'm not going to want you to, I am not going to need this proof. And then you write this in terms of determinant. And then from there, you dot it with this vector. Therefore, you can actually see that the divergence of a curl is always 0. And I hope this is what you know from your previous maths class. Right. Now, putting the electric field into equation 1. Putting the electric field into equation 1, because now we know that the Maxwell equation 1 is giving us the divergence of the electric field. The divergence of electric field is rho over epsilon naught, and we know what is the electric field in terms of the scalar potential, and then in terms of the vector potential A. So this is your electric field. Now whenever I see the electric field, this is what I'm going to write. Now I'm having the divergence. The divergence of the electric field is the negative gradient of V minus dA dt, and that must be equals to rho over epsilon naught. Now in that case, this and that one is just going to give me a negative Laplacian of the scalar potential minus, this is just going to be d dt, and then this is just going to be the divergence of A, and that must be equals to rho over epsilon naught. But in here I can multiply by negative there. This will be positive, this will be positive, and this will be negative if I multiply by that. And that is this equation that you are actually, this is that equation that you are actually seeing in here. And this is actually the similar to what is formally known as the Boison's equation. You remember the Boison's equation. The Boison's equation, when the divergence of A is equal to 0, therefore you are just going to have what? When the divergence of A is equal to 0, therefore you are just going to have the divergence you are just going to have the Laplacian is just equal to negative rho over epsilon naught when this is 0. So that's basically what I will be talking about in the next few minutes. Yes, this is reduces to the Poisson's equation in static case. Because in static case, this was just derived in the previous chapters from the previous classes. Now, putting both E and B into equation 4 yields, I put both E and B in equation 4. The curl of B, instead of writing B, I'm going to write this. The curl of that is just given by the E. Now, whenever I see E, I'm just going to write this. Now, if you put that into that equation, this is what you are going to have. This is what you are going to have. Right. Now, from there, I'm just going to use one of the vector identities, which states that the curl of a curl is just given as the gradient of the divergence of that vector minus the Laplacian of that vector. Right. Now, in that case, and after that, I rearrange the equation. After rearrange the equation, this is what I'm going to have. This is what I'm going to have after using that. And if this is the case, now, from the Coulomb's gauge, in magnetostatics, of course, if the divergence of A is equal to 0, therefore, this equation here, this term here will just vanish as I've shown you. And therefore, I will just, this equation there will become the Poisson's equation. This equation here will becomes the formerly known as a Poisson equation in static case. All right. Now, the differential equation, the previous differential equation, if this one goes to 0, this is what we have for this, and this term will just vanish because this divergence is equal to 0. Therefore, this equation can be written in terms of this equation. Because this term is this term, this one is this term, but this term here will just go, this term here will go, but this last term there will still exist, and then this term again is this one here. Right. Now, from the Lorentz gauge, we pick that the divergence of A, the divergence of the scalar potential, of the vector potential A, is just given by this. Now, if we put that in this equation, this term here will go. This is what we know. This term here will go, because this is just going to be this term, which is the same as this term, but this one is positive, this one is negative. Therefore, the whole term there will just go. And then, if that is the case, then we are just going to have this term here, this term here. This is the term that we are going to have, and this term there that we are going to have, and this is the other term that we are going to have there. Right. Now, therefore, the potential is just the Laplacian of this this equation here will just become this equation here. And as you can see, this equation here looks like the wave equation. This is just like the wave equation, the second order a wave equation, where this term here, it can be related to the speed of light. As you still remember that the speed of light is nothing else but the speed of light is just given as 1 over mu naught epsilon naught. So that is your speed of light. Good. So now from there we can actually use what you call an operator. If we take out this operator here, this operator which is defined as this the square, this sign here and square, and that is what we call the Albertian operator. So that's what you are going to have if you want to write that in terms of the D'Alembert operator. This is what you are going to have for the scalar potential as well as the vector potential. So we have two equations here which are actually for the potentials, which are actually showing that they are the wave equations. Now, with that, we can see that the scalar potential and the vector potential satisfy an inhomogeneous wave equation with a source term. The source term, which is the charge density or the current density, is just given on the right. So this is nothing else but this is an inhomogeneous wave equation. Right. Now let us just talk about the solution of this inhomogeneous wave equation, because this is what we have seen. This is what we have derived in terms of the 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 the, the scalar potential and the vector potential. Now these are an expression of Maxwell's in terms of the potential and using the Coulomb's gauge. Now in this case, in order for us to have this, the first we need to consider the static vision. The static vision, this term here will just vanish, this term here will just vanish, and then we'll end up with this equation known as a Bayesian equation. Now in that case, in the static case, the solution for the potential was just given by this. Now in this case, remember, the potential was just a function of the position. In this case, we want to get the general solution where the potential is the function of the position and the time. Now if we look at that, now where this R was just nothing else but the separation vector, I just want to remind you that R is the separation vector. For an example, this is a vector, this is the R vector prime, which is the source point, and here we have the field point. The field point is denoted by this R, small r vector. Now this vector in here, that vector here is what we call this big R vector, and in other books this is just written as this R is written as this. Now when I want to use the tail to head method, you can just see that this vector here, this vector R is just given by R prime vector plus that big R. Now if I want to make that vector R a subject of the formula, the separation vector, I'm just going to have that vector, the source, the field vector minus the source vector. So this is what you are actually seeing there. So this is nothing else but the separation vector. So from the previous studies, you know that this is the source point. This is the source point. This R prime represent the source point, while this R vector is nothing else but the field point where the field is going to be measured. Now this R here is nothing else but it's just the separation vector. Right, now this R here is just given by that. All right, now if we consider the full equation, in homogeneous wave equation, the left side is you have the additional of the non-static case, which is this term here. Now this will actually force us, because we can also see that there's a speed of light there. This will force us to incorporate the idea of this speed. This inspires us to guess a possible solution for the potential for the non-static case, and that potential is just given by this equation. There you just put the time factor, and then here you also put the time, where this TR is nothing else but is what we call the retarded time. But at an earlier time, or the retarded time, therefore this is what you are going to have, where the charge density is just given by this is the charge density at the source point. This is the charge density at the source point, as I've shown you, but at an earlier or time or retarded time. That's why this is TR, and TR is just given by this equation, T minus, because it takes time for the electromagnetic wave to move from one point to the other, from moving from the source point to here. Therefore that T is actually the retarded time. The earlier time is just given by this. Now we can get time. What is T? T, it will be the retarded time plus R over C. Yes. So that's what I wanted you to see. Right. So now in this case, as soon as we have this as our potential, this is what we are guessing. Now we just want to see that this potential satisfy the wave equation formerly known as the Bayesian's equation. We want to see that this potential will be able satisfy this. Now, in order for us to do that, we will have to take the second order differential of this potential, and then we differentiate that potential with respect to time, and then we see what we are going to have. But now, before we do that, I just want to remind you the basics results of vector algebra, and I will not want you to prove for an example. The first one is the gradient of R. The gradient of R is just the unit vector R. The gradient of R is just the unit vector R. Now, I'm just going to start, this is the only one that I will just be proving, because I'm going to present many to you, is just the unit vector in R. But what is R? Now, I know what is the retarded time. Retarded time, I've just defined retarded time as that R over C. Now, if you want to make R a subject of the formula, what are you going to have there? You are just going to have R is equals to T CT minus CTR. Right. Now, this is what you are going to have for your R. Now, if you take the gradient there, if you take the gradient of R, therefore it will mean that you also take the gradient there on this side. It will mean that you also take the gradient on the other side. The gradient of R, therefore, will just be nothing else, but this can just, because this one is just going to be 0, therefore this is just going to be minus C TR. So this is one of the equations that you will be seeing there. Right. Now, this is what you are going to have here for the gradient of 1 over R, and then this is what you are going to have for the divergence, or the divergence of R. It can be defined in terms of the Dirac delta function, and you can also have the divergence of this to be 1 over R squared, and you will also have, we are also going to use the product rule. We are also going to be using the product rule. If you have to differentiate two functions of function f and g, this is what you are going to do. And from there, you can also write this, the divergence of this vector time is the scalar function to be given by this. Now, what we are going to do, we are just going to, first of all, to take the first derivative of this potential, and then from there, we are going to take the second order. After getting the answer of the first derivative, we are going to take the second order differential or derivative, which is nothing else but the Laplacian. Now, first of all, we just want to obtain this, but before we can obtain that, we need to compute first the first order differential of this. Now, if we do that, this is what we are going to have. But this del goes to for an unprime, because the integral goes for the prime coordinates. Therefore, this del will just be getting inside here. Now, if you put that del inside there, and then you use the product rule, you differentiate, you leave the charge density, you differentiate 1 over R, plus you leave 1 over R, you differentiate the charge density. This is what you are going to have. And then from there, we know what is the gradient of 1 over R. The gradient of 1 over R from the results, the definition of the result of the vector algebra, this is what you are going to have. Therefore, I'm just going, whenever I see this, the first term here is just going to be given by this. This is just going to be minus the unit vector R divided by R squared here. But what is this? What is this? This is what I want to solve now. I want to tackle the second one, can be tackled using the chain rule twice. First of all, whenever I see the del, I'm just going to write this, and then again, I'm just whenever I see the partial differential with respect to the retarded time, I'm just going to write the partial of the partial with respect to time, like this. Now, this is what I'm going to write. Whenever I see del, this is what I'm going to write. I'm going to write, this is the charge density. You have the charge density there. You have the charge density there. But I need to take the product rule. I'm also going to take the differential of this TR. This is what I'm going to have. Now, whenever I take this, in terms of this, I'm just going to tackle this by taking the chain rule twice. Now, I'm going to take the chain rule twice. Whenever I have this, I can just take the chain rule twice, when I take the chain rule twice, I'm going to multiply it by the, okay, let me just do it for you. I'm just going to take this, and then in here I have this r vector prime tr. Now if I have to take this differential there, what I'm going to have, I'm just going to multiply that by, I'm just going to take the differential here with respect to the retarded time. That's the first one. I'm taking the differential with respect to the retarded time, and then from there I'm making the chain rule. I'm taking with respect to the retarded time. This is what I'm going to have. And now if I have that, this is just going to be d with respect to retarded time. Let me just write rho. I'm just going to leave this term there, and then from there I'm just going to have what? This is what I'm going to have there. I'm just going to have tr. Now from there, if I have tr, I can just use, this is what I'm going to have there. This is what I'm going to have there. Then I can actually change the order. I can therefore multiply this by dt, and then from there move this here and exchange that with that here. So this is what you are going to see here. This is what you are going to see here. So good people, this is very, very simple. All you need to do is to actually write it a little bit down. So that's what you are going to have. Now, substituting the retarded time, the definition of the retarded time is this is what you are going to have for this. This is what you are going to have. This is what you are going to have. Whenever you see the t, whenever you see t, I'm just going to write the definition of t. If you make a t subject of the formula, this is what you are going to have here. And then the derivative of this, the del for the tr is just given by this. Now from there, if you do that, for an example, if you differentiate this, this with respect to tr, this is what you are going to have 1. You are going to have 1. But this one is just going to be 0 because you don't have tr with this one. The second term there will be 0. That's why you are not going to have that. This, the whole thing here is just going to be 1 because the other one is just going to be 0. But now the derivative of this t with respect to the position, this is just going to be 0, and then this is just going to be the derivative of r with respect to c. But we know what is the gradient this. We know what is this. Now from there, we can just write this in terms of this equation because we know what is the gradient of r. The gradient of r is nothing else but it's the unit vector r from the definition. Now from there, we can put things together, and then we can just write that whenever we see this, this is what we are going to write. So this is what you are going to have as your potential. Now from there, remember, we want to take the second order of this. Now we take the second order differentiation of this potential. Now this is what you are going to have for that. But this then will always be moving inside because the integral is for the prime while the del is for the unprime. So this is what you are going to have. This minus there is that minus there. And then this term here is this term there. That term there is this term here. Right. Now, I am going to be working on this as the first term. I will solve the first term first, and then I will also solve the second term, and then from there put things together so that I can find the final equation for the Laplacian of v. Now, in that case, let me solve the first term first. Now, if I solve the first term first, I am using the product rule here. I leave the charge density, I differentiate this, and then I leave this term, and then I differentiate the charge density. But we already know what is the results for this. We already know what is the result for this. And this can be given from the result of the vector algebra. The result of the vector algebra, this can be written in terms of the 4 pi, the Dirac delta function. And then that is just given by that. Now, in that case, we can also go and simplify this term here. This term here. Now, if we simplify that term there, this is what we are going to have. If we simplify this, this is this. And then this term here, this term here, it can actually be written in terms of this. Why that is the case? Because we have r dot r. Now let me just remind you the dot product of two vectors. If you have r dot r, these are unit vectors. It can be given as the magnitude of unit vector r and the magnitude of the unit vector r and the cosine of an angle between them. What is the angle between them? This unit vector, the angle between them is just equals to 0, and the cosine of 0, the cosine of 0 is nothing else but is just given as 1. So as a result, this r dot r will just give us 1, and as a result, that's why you will see this here as 1 divided by this r squared and c. So that's what you are going to have. Now, solving the second term, this is for the first term. This is for the first term, which means for the potential, don't remember, I would still have to multiply by 1 over 4 pi epsilon naught, the volume integral d tau. This is the first term that I'm going to put. Now, when I solve the second term in here, I'm just going to leave this and differentiate this. This is this term, and then I leave this, I differentiate that. This is what I'm going to have. Now, in that case, this is just going to be equals to this, because I know what is the divergence of this from the definitions. The divergence of the unit vector divided by r is nothing else but 1 over r squared. Then you have that c as a constant there, plus this the gradient of that. But we have already solved this. From the previous slides. So now that can be given in terms of this. So that can be written in terms of this. I can write this upside there, and then this is what I'm going to have there as minus, because I know what is this. I've already solved it. Now this term there will just become minus this, because it's positive multiplied by negative. I'm going to have minus there. So this is what I'm going to have. Now that is the solution of the second term. Now I combine the first term there and the second term there, so that I can be able to write the Laplacian of the potential. Therefore, this is the answer. But now this term here is the same as that term. They will cancel. Now if they cancel, the potential is just given by this. But I can even solve it a little bit further, because this is the d tau. I can actually split this in terms of the d tau. I can put the d tau here. If I put the d tau here, I will have to write 1 over 4 pi, the volume integral d tau here also. So now this 4 pi can cancel this 4 pi. And then that's what you are going to see a little bit later. So I can split that to write d tau, these terms separately, and then I can have this as a d tau, 4 pi, because the argument is there. But now if I want to put the argument there, therefore I will have to write this in terms of that. And now this 4 pi will cancel this 4 pi. And from there, this is what you are just going to have for that equation. Now I want to factor out this and then write this, because what is this? This is what we have said is the potential. This is the potential. Now if that is a potential, therefore I can write this in terms of this. I can write that in terms of this, where r prime is r vector. This term here will just vanish, and then I will end up with this. Now here, whenever I see this, I write the potential, and that must be equals to this. This must be equals to this, because this term here is nothing else but it's just the minus rho, because this is nothing else but it's the retarded time. This is when r is equals to this r. This would just vanish. I'm just going to be left with this r as a function of this t only, because r prime is equal to r. I'm going to have 0 divided by c, which will vanish this term, and then I will end up with this over epsilon naught. But that must be plus this potential. Now what is that? Hence, this potential that we have suggested, or that we have assumed, is a solution to the inhomogeneous wave equation, because this is just this is equals to that. Right. Now likewise, a vector, the vector potential A is a solution to inhomogeneous wave equation. This can also be shown, and therefore this is just the case. Therefore this are known as the retarded potentials, because these are the potential taken at the retarded time. Right? This equation here and this one here are what we call the are known as the retarded potentials. Now let us also dive into Jeffimenko's equation. Now, because we know the retarded potential, we've just derived them. Now we can be able to obtain the electric field in terms of the vector potential, because we can take the gradient of this and plug it there, and then we can differentiate this with respect to time, and that will be the electric field, while the magnetic field will be taken as when we compute the curl of A, because we only take the curl of this. Right, let us just start with the electric field. Now, when we start with the electric field, we already have shown that the gradient of V is given by this. This is the gradient of V. Now, what we need to do, we need to take the time derivative of the vector potential A. Now, if we take the gradient of the vector potential A, this is what we are going to have for the gradient of the vector potential A. Now, this term here is just written in terms of, you still remember that when I have the C squared is equals to 1 over mu naught epsilon naught. Now, in this equation, you have mu naught over 4 pi. I'm just taking this first part here, only this first part, so that I can show you this is this case. Now, in that case, you make mu a subject of the formula. When you make mu a subject of the formula, in this case, what are you going to have? Mu naught is just going to be 1 divided by C squared epsilon naught. So now, whenever you see mu naught, this is what you are going to write. Whenever you see mu naught, sorry, this is what you are going to have. Now, if you do that, this is what you are going to have for that time derivative of this. But the time derivative will only go for here inside, because the prime is the integral goes for the prime. Good. Right, now from here we can be able to write, therefore we can be able to write the electric field. We write the electric field because we know the gradient. This is the gradient. This is the gradient of scalar potential minus this term here. That this is the term here, and then I'm just factoring 1 over 4 pi epsilon naught. I'm just factoring 1 over 4 pi epsilon naught. Now, that is why I'm actually using this mu naught. I want to write mu naught in terms of the epsilon and the C squared. So that's why now I'm factoring this out, and this is what I'm going to have for the electric field. Now, what is the magnetic field? Now, the electric field, if we want to use, whenever I see the time derivative of a certain vector, I want to use this notation. Whenever I see the time derivative of a certain vector of the certain scalar, say P, I can just write this as P dot. So now whenever I see the time derivative of the rho, I'm just going to write, I will just assume that you know that this is taken at the retarded time. So now this is what you are going to have there. Whenever I see, now I'm just writing this equation, I'm just going to write this rho, and I assume that you know that this is taken at the retarded time. Now whenever I see this term here, plus this term, whenever I see rho, and then I'm seeing the differential, I'm just going to write rho dot. And then here I'm just going to write J dot. So this is what I'm going to have in terms of the electric field. Right, now let us also talk about the magnetic field, because we have found the electric field. The magnetic field is just given by a curl of A. Now the curl of A is just going to be given by this. Now the curl will only go for the unprime coordinate, so that's why I'm putting it inside here. Now in that case, when you take the curl of J, this is what you are going to have. Let me just remind you, maybe for 1 second, that if I want to take a curl of the curl of J, the curl of vector J, this is nothing else but in terms of the determinant, this is the in I, and then this is in the unit vector that. The first one here is this one here, dx, dy, dz, and this is here, the last one here, jx, and then jy, and then jz. Now, if I want to compute this only in I, only in I, what I'm going to have there, I'm just going to have dy, this is that, multiplied by that, and then jz minus that multiplied by that, the dz jy. So this is only in I. Therefore, you can also compute the others in j, and then plus others in unit vector k. But for now, I'm just going to solve only for x, and then after solving for x, I will write the general solution for everything, because what I'm going to apply here is the same thing that I'm going to apply here in order for us to save time. So in that case, so this is what you are seeing in that equation here. So this is what you are going to see in that equation here. Or in fact, before you do that, now you take the cross product. Now if you take the cross product there, this is what you are going to have. For that, you take that and then you leave JR, and then you take this, and then from there you can write this one over R, that, but you know what is this? That is just given by this term here from the definition of the vectors. Now, if we tackle the x component only, because now you see, I want to take the curl of this, and then I only take the x component. If you do this, this is what you are going to have for the x component. Now, this is what you are going to have for the x component, and this term here is nothing else but this is the same thing here. This is just the same thing here. Right, I hope you are able to see that. Right, now from there, when applying the chain rule to change the differential variables, if I want to change the differential variables, I can multiply by dy, I can multiply these terms. I can multiply this I can multiply this with the, sorry, I can multiply this with dr divided by dtr, and then change the order there, and then move this one there, and then move that other one there, and then apply the same in this one. So that's what you are actually seeing here, and then you apply the same for the other one. Right, now when we change the variables again, when we change the differential variables again and substitute that tr is equal to this, this is what I'm going to have. This is what I'm going to have. Now for the second time, what you do for the second time, you multiply that term. Let me just write it here. You have, I'm just talking about this first term here. You just have this dtr, and then you have jz, and then in there you have the dtr divided by dy. Now in that case, I also want to change the variables. I'm going to multiply by dt over dt, and then move this one there. Yes, I want to move that one there, and then move that other one, and change this one, and move it there. Right, and this is what you are actually seeing in this equation here. So that's what you are going to have. So that's the calculus of it. Now from there, if you differentiate this with respect to y, you are just going to, you differentiate r with respect to y. This one, you are just going to have 0 for this one. Now this differential will only go for this, and you are going to have -1 over c squared. Even in here, the differential will just, this one will be 0 because this is t, is a constant, differential with respect to constant, but here r, when you open r inside, you will have z. So now this is just going to be 1 over c squared. So now you can write this equation in terms of this. Now when you look at the numerator, and of course this is just going to be 1, and when you look at the numerator, this is just going to be 1, and that is just going to be 1. Now when you look at the numerator can be written in terms of this, in x, and since this, the gradient of r is just in unit vector r, therefore in that case you can just write the general, this is in x. Now if you want to write, you apply the same for y and the z, and the general solution for this is just given by this equation. That is the curl of j, the current density is just given by 1 over c, the time derivative of the j at the retarded time cross the unit vector in r. Now putting things together, therefore magnetic field is just given by this equation here. It's just given by this equation here. It will therefore be given by this equation here. This can also be written in this fashion, because whenever I see the time derivative, I just want to write j dot. So this is what I'm going to have for the magnetic field. Now let us also discuss the potential of a moving point charge. Now the inhomogeneous wave equation is just given by this. This is what we have derived, and we have seen that this is the case. Now the expression of Maxwell's equation in terms of the potential and using the Lorentz gauge. Now in that case, the potential, their solutions are given by the scalar potential and the vector potential, like that. Right. Now the separation vector, the magnitude of the separation vector, you remember I told you earlier on that that vector, the separation vector is nothing else but is that source vector minus the field vector minus this. These are just the vector. But now when I'm taking the magnitude, the magnitude of this vector r, I can just write simply r. That is the magnitude of, I'm going to write this in terms of that. So that is the magnitude of r. And from the definition, we know what is the retarded potential. We know what is the retarded time. The retarded time is just given by this equation here. Now, what we wish to do is to find the potential of a moving charge, and that is nothing else but the linear Wichart's potential. Now, we wish to apply this to a single point charge moving in a trajectory omega, the vector, the position omega r, to obtain the potential of a moving charge, which is nothing else but this is just the linear Wichart's potential. Now the charge density for such a point charge is just given by this. It can be defined in terms of the Dirac delta function. It can be given by this. But at the retarded time, the charge density will just be given by this at the retarded time. So this is what you are going to have as your charge density. Now, as a result, we know what is the potential. Now we know what is the charge density. We are just going to plug the charge density there. Now this integral is still there. That q is just a constant, is outside there. Right. Now we can also change the order of the integration. If we change the order of the integration, this is what we are going to have. We change the order of the integration. We change the order. This is dt and then the d tau there. Now if we want to change the order of the integration, this is what we are going to have there. Right. Now in performing the special integration, and we take the r prime to, it goes to be this, because this is what we call the projection of that charge moving the trajectory omega, the w vector w at that specific time t prime. This will just produce this, because if r prime goes to omega, therefore this term here will just vanish, and then we'll just be left with this term here. And we know what is the retarded time. The retarded time, therefore, it will just be written in terms of this whole equation here. Right? This r, the magnitude of r is nothing else but it's just given by this, as I've shown you. Right. Now to perform the remaining integration, we make the change of variable. Now if we let this everything here to be equals to u. If we make everything here to be equals to u, and now if we take the d, we want to take the du with respect to d prime. Now d prime, if we differentiate this with respect to u, is just going to be 1, but this one is, this minus is this one here, the 0 here, because this is not t prime, it's only t, therefore it will be 0. And then you differentiate this, it is just going to be 1 over c, you use the chain rule, 1 over c, you chain rule, you differentiate also this magnitude there. Right, therefore this is just going to be 1 minus 0, and then this is what you are going to have for that. Now, what is the result for this? I just want to show you what will be the result for this. Now consider, by definition, if the square, if we have this square magnitude, it's just given by this, and then we take the differentiation, you differentiate both left and the right hand side. Therefore, if you differentiate that, that is just going to be 2, and then chain rule, you differentiate that again, and in here you are just going to have 2 and that and that, and then you take the differentiation here, this is just going to be 0, and then you differentiate with respect to t. This is what you are going to have there, right? But now if you want to make this a subject of the formula, therefore this term will, 2 will cancel this, and then you will divide this by the magnitude here. You will have to divide this by the magnitude, and then this one will be 0, and then multiply by that. But now we want to define this as a velocity. As a result, so this can be written in terms of this. What I'm trying to do here is I want to make this a subject of the formula, this term here a subject of the formula. Now if I do that, I'm going to divide by this 2 magnitude of r, and then I'm going to divide by 2 magnitude of r. Therefore this 2 will go, but this is a vector, it cannot cancel the magnitude, that's why you still see it there. And the definition of this is just this one here, right? Now therefore, if I have this is just going to be given by 1 minus this term here, which is this term here, right? Now from there I can go take this and then put it back to the equation of the potential. Now in the equation of the potential, this is what I'm going to have. This is what I'm going to have. Now I want to write this in terms of the delta u du. Now this is this term here, this is this term here, that is this term here. Now what I also want to show you is the fact that this term will multiply by 1, and this term, when it multiply this second term here, it will cancel this, and then the only term that will be left is this one. Now this is what I'm going to show you in the next slide. But before I do that, now if you let u is equals to 0, if u is equals to 0, it will mean that if u is equals to 0, if u is equals to 0, it will mean that this t prime is just equals to the retarded time, right? So this is what you are going to have. Now that will just be equals to the retarded time. Now instead of the tr, you write this specifically tr is just going to be, and then if you perform the temporary integration, this is what you are going to have. Now if you multiply this by 1, this is what you are going to have. But if this one multiplies here, it will cancel this, it will leave 1 over c squared, 1 over c, this vector, not multiply by that, and this is nothing else but this is just equals to this, right? Now let me just remind you again so that you can see how did I come up with this. I am defining the vector r as that vector minus that vector, right? Now the magnitude of r is nothing else but it's just going to be magnitude of this r minus the trajectory. So this is what you are going to have. So that's what you are seeing there. Now instead of me, whenever I see this, I'm going to write this vector. Whenever I see this, I'm going to write this I'm going to write the vector r. Whenever I see this magnitude, I'm just going to write r. Now, when you look at this equation here, what is this? This is the magnitude of r. That's why you see the magnitude of r. Now, if you solve this, you will see that there will be a c here. Now, whenever I see this, that c will go up. Therefore, we'll just go for this other term. Now here, whenever I see this, I'm just going to write r vector. Whenever I see this, I'm going to write r vector. Right. So that's what I want you to see. Right from there, we've got the potential, and therefore from the r is applied. This is what I've just shown you, and now the vector potential can also be given in terms of this. So this is just going to be the vector potential. Now from there, these potentials are what you call the potential of moving point charge, what you call the linear charge potentials, and are just given by these two equations. Right. Now, since we have the potential of a moving point charge, we have the potential, the scalar and the vector potential. Now, whenever we have the potential, therefore we can be able to get the electric field, because the electric field is given by a negative gradient of the potential minus the d vector and then dt. And then the magnetic field is just given by the curl of a vector as a vector potential A. So we know the potential, we are just going to take the gradient of that potential, and then we differentiate that a vector potential, and then here we just take the curl, and therefore that will help us to compute what you call the electric field and the magnetic field. So that is what we want to do now. Now, we have the potential, therefore we can be able to get the fields of a moving point charge. Right. Now, we take the gradient of V. Now, if we take the gradient of V, this is what you are going to have if we take the gradient of V. Now, what is very important here is the fact that this RC, I'm just going to talk about this term because the differentiation is just going to go for this one. Now, I'm going to take that term to be a numerator. When I'm taking it up, it's just going to be RC minus R vector dot V is going to be minus 1. Now, if I differentiate this, that, this is just going to give me minus 1. But the same term here, RC minus R vector V, but here I'm going to have minus 2. So this is what you are seeing here. And then from there, I'm taking a chain rule. I'm differentiating this again. This is what you are seeing here. Right. So that's what I want you to see. So this is what you are going to have. Now, if you do that, this is what you are going to have. Now you take it back to be the denominator, and this is what you are going to have, and then that will just be this. But that term here will be minus because of this minus multiplied by this is minus. This minus multiplied by this is just going to be positive. So that is what we are going to have. Now I want to solve this. What is this? What is this? Now I can write this in terms, I'm going to differentiate, I'm going to leave C and then differentiate the minus R. And then from there I can write this in terms of this vector identities. So this is what I'm going to have for this other term. Now I want to apply the following, and the proofs for this will just be given later. In fact, I've already shown you what is this one here. I've already shown you the gradient of R is just given by negative C delta R. So, and all others are just going to be given a little bit later. So for an example, if you have the gradient of R, but what is R? We know what is R. R is equal to what? The R, the magnitude of R. Now, we are just going to have the retarded time is just given by T minus R over C. Therefore, R is just equals to T CT minus CTR. That is your R. Now, if you take the gradient, that will mean you will be taking the gradient of Ct minus Ctr. But the first term here, this one will go to 0. 0, and then you're left with the gradient of, and then I want to write C here and a negative there, and then Tr here. So that's why you see this. So, and all others will just be proven, and then the proofs will be given to you later on. Now, I want to use this in this equation here. So now, for an example, when I see the gradient of R, I'm just going to write the gradient of R, I'm just going to write this. I see that, therefore that will be C squared, and then the gradient of R is just this. Therefore, that will be C squared. So this whole thing will just be given by this equation here. For an example, whenever I see this is the R cross the curl of V. What is the curl of V? The curl of V is given by this. This is this R, this is that R, but the curl of V is just given by this. The curl of V is just given by this. Right. Now the curl of R, what is the curl of R? So the curl of R is this one here. So now if you put everything there, this is what you are going to have. And then from there, you can just simplify this a little bit further. And now you can also see that this term will cancel this other one, and this term here will cancel this other term. Now from there, you can eventually write the gradient of the potential in terms of this. This is the gradient of the potential. And when you use when you use this, you can actually write this in terms of that. Now the potential will therefore be given by this. Now we know the gradient of the potential. Now what we need to do is to take the time derivative, because we want to get the electric field. The time derivative of A. You use the chain rule there. If you use the chain rule, this is what you are going to have there. Now you use the chain rule, you differentiate the potential with respect to T. Differentiate the potential with respect to T. So this is what you are going to have. Now you have this is what you are going to have. Now that will be plus the other term where you have the potential, and then this is what you are going to have, dv dt. Now from there, when you are having that, this can actually be written in terms of this. Now we also want to apply the proofs. Now from there, I can factor out the dv dt, this in that equation. Therefore, this is the v. This is what I'm going to have. Now we apply the following, and the proofs will be provided later, that if you have this, you can write that, and if you have this, you can write this. So now in that case, if you do that, this is what you are going to have. Now from that equation, you can actually factor this derivative. You can factor out this derivative for everything there. This is what you are going to have. Now from there, if you use number 10, here, this is what you are going to have for the time derivative of the scalar potential A. Now from there, this is what you are going to have for the. Now if you know the time derivative of the vector potential A, you can plug it into the electric field. Now therefore the electric field will just be given by this equation here. That is the electric field of a moving point charge. So that can actually be written in terms of this. When we have done that, this is what you are going to have. Now if you define the vector U as C, the unit vector R minus V, so that when you take R dot U, it will give us CR. It will give us CR minus R vector dot V. Right. So that's what you are going to have in there. So but now this is the dot, this R. What is this R? What is this R? this R vector. Now this R vector, yes, you can actually easily show that this is the case, because this is U. You write the U. The U is given by this. Now let me just do it for you here. R dot U, R dot U, but now this is R dot, I'm going to have C unit vector R minus V. What is this going to be? The R vector dot this, the R vector dot this is just going to be CR. The magnitude here, this is just the magnitude. And you can actually use the unit vector is nothing else but it's just the R vector divided by magnitude of R. And then that will be minus R dot V. So that's correct. So that you have that. Now in that case, the electric field will just be given by this equation here. And then from there, using the product rule, in order for us to get the magnetic field, this is what we are going to have for the product rule. Now from that, you can just see that the curl of V is just given by this, and it's just given by that from what we have defined. But what I want you to see is the V cross V is just going to be 0. That means this term here is just going to be 0, because V cross V, the cross product of two vectors, remember the cross product of two vectors, the cross product of two vectors, the cross product of two vectors cross V is nothing else but is the magnitude of V multiplied by the magnitude of V, and then the sign of an angle between them. The angle between them is just 0. Therefore the sign of 0 is just equals to 0. Therefore V cross V will just be 0. As a result, that term will just vanish. Will just vanish to be 0. Right, now this will just be 0, and then this term here is V minus multiplied by minus is just going to be plus V cross this term. Right, so that will be your magnetic field. Now since U is just given by this, we have R cross U is just given by this. Now you have U is given by this. R cross U is just going to be given by this. So now this is also simple, because you have U, R. I want to show you that R cross U, I'm going to have C minus V. Therefore in here what I'm going to have R cross that. I'm going to have this R cross the unit vector R. The angle between R and the vector R and R is just going to be 0. Therefore you are just going to have 0 there. That will be minus R cross V minus R. That will be minus R cross V. That will be minus R cross V. But the R cross V is nothing else but it's just V cross R. So that's when you interchange this from the product rule, this is what you are going to have. Right. So that's what you are basically going to have for this one here. Now from there, the magnetic field can be therefore be given by this equation here. Now B will always be given by R unit vector cross E, and this is actually telling us the B and E are perpendicular to each other, and they are perpendicular to the motion to the magnetic field of the point charge is perpendicular to the electric field and to the separation vector from the retarded potential. Now with all that, good people, I would like to just pause there, and I apologize for the lots of calculus. Thank you. Goodbye.